Thank you for inviting me in this nice workshop. My discussion will be about a mobility network model that make use of latent variables as some application to real world data. Let's start with the question why we are here. Essentially, we would like to explain some patterns of movements of people in visiting the location of interest. Let's start with the purposes that actually are introduced what is called an homogeneous graph made up of latent variable. So that we go through the stochastic process that describe the visits in location. And we get also, I will show the scaling laws of mobility that is a pretty important stuff. And then as a target, specific target, I will show how to a possible way to infer latent variables from data that can estimate the patterns of mobility starting from these latent variables, and then compare and predict with the observed visiting. And finally, some economic property will be highlighted as a consequence of those scaling laws, for example, in elasticity of income travel. Let's go to introduction of travel demand as a network. Essentially, the reason why people move is because they want to be better, so go from scarcity to well-being. So people move because they need for something. So, and we will just highlight how far, how frequently people move to different locations, this kind of stuff. And they are important for many practical reasons, the social, consumer choices, how cities develop, and so many other issues. We start with the description of a city. I call it the selection. There are cities can be split in different areas that usually are census or administrative areas in a region. So it's, and we have for all the tiny region of a city data that can be taken from census bureau offices. So for example, social and economical conditions, or you can get from GPS cell phones, as Luca was saying, using some of data providers, like Google, Foursquare, also TomTom. There are many. And let's imagine that each area is well called block sometime or location have a couple of important issues. So is what is called travel purposes. So what is important is the population that lives there, or at least the active populations, because there are differences that in some sense produce travels. And then there is another property or attributes of location that I will call attractiveness, that is related to job opportunities, parks there. So it's the way a location can attract new visits. And they will call location attractiveness, that in some sense is a travel demand driver, okay, what is called like in economics like that. The analytical side, so I will present briefly, I will skip if it's too long, let's say. I have to check detailed. Okay, so this is different way to describe a network of mobility. You can go from macroscopic to macroscopic. Essentially, I will work with a mesoscopic built model, and then I will go to variables that are macroscopic. Okay, the microscopic one is about traffic, trajectories of individuals. Okay, you can change the granularity of your model. Essentially, I have a visitation graph. So it's a directed graph where nodes are the locations, the urban blocks area. We have directed edges because you can go from one location to another or differently. And each trip can be assigned in terms of weights or costs, no, of each trip of a visit. And then the graph can evolve during a day. For example, this is a daily description. So every time there is a new trip, there is a travel completed, I connect and two locations. Okay. And this is fully described by a time-dependent origin destination matrix. So essentially, we start with a tessellation graph again. So I will assign to each location to be a node of the network. They are not non-overlapping. And for those nodes, I build this inhomogeneous random graph that is specified by the following assumption. Say, the first assumption that each location, for each location is labeled by this attractiveness or a property. This property represent latent variables that can be represented as identically distributed random variables, so that obey to a distribution function. So latent variables are the hidden drivers of the graph generation. Then we have the movements, say the process of producing trips that is driven by what is called arrival rates. So you have a kernel function. This is the pointer. This the pointer is also. Okay, this is a KXY that is also more popular in literature that represent is connected to the probability that from a location of population Y can reach a destination of attractiveness X. And you can build what is called the arrival. In the arrival process, you can build the infinitesimal arrival intensity that gives you the rates of new arrivals of the visits in each location. A part of then I have the trip cost definition. So I have the links here. Then the links are weighted in the sense that each trip has a cost, and this cost is assumed to be independent from the process of creating links, and also is a random variable itself according to a distribution, rho x in this case. For example, the cost can be assigned in terms of distance traveled, okay, different distance travel or travel time, or the cost that you pay to go from one location to other, or the emission, as Luca was saying before. You can associate a cost to each of them, each trip. So in general, we can build a graph configuration that the adjacency matrix, but I will just stretch the attention, focus the attention of the degree distribution, so the visit distribution of the weighted counterpart, and also the correlations, the spatial correlation in space. Okay, so we go from graph configuration to what is the visit generation or the trip generation when I'm focused on the arrivals, and then we will see what happens. So essentially, you have three important, three important variables. One is the attractiveness distribution, so how location are different attractive in the city, for example. This attraction rate that depends on how one individual moves to places, and then the travel weight. We have three variables, and they shape the visiting patterns. This is the model that it should be then compare with the observation later. And I just briefly sketch the dynamics as a stochastic process. I have a integral differential Kolmogorov equation. Is a sort of master equation with jumps. Jumps are the trip cost. Okay, each trip is not one, but it is weighted for its particular cost or weight, and they can be solved, and then we can reach a sort of almost bounded normal distribution in asymptotic limit for each. So this is the master equation of, as you can see here, is the master equation for all the location that has a given attractiveness. Okay, is a conditional to have a certain attractiveness. Then I can compute those conditional distribution for all the possible attractiveness in the region, and then I can compound or mix them in order to have what is called the full visit distribution that can be calculated according to the choice of the probability, the arrival rates. This is a general. For a particular choice, this is equivalent for many individuals that work on finance. It's equivalent to a compound counting process, where arrivals are actually weighted with jumps. You can restate everything in terms of a compound counting process. Then you can have the same calculations of the characteristic function, the distribution, but quite general. In the other case, I have a real value probability distribution to simulate. Okay, but it's equivalent. Then I can calculate graph correlations. Graph correlation, there are many correlation graphs. I take the most common ones, the assortativity. So it's if nodes are related to nodes that are similar in, for example, in a type of property of the cluster coefficient. That is the ability that your neighbors are also neighbors among them. So I can restate graph correlation in terms of the rates. It is key is the conditional probability that a visit in a destination of a given attractiveness has originated from a location of a given population. So you can restate the correlation in terms of this variable that is expressed by the same property of rates of arrivals. This is the generic computation of a directed. In the case the origin and destination are independent in sense they are just plain random. Okay, everything is more simple in the calculation, and I get very easy estimate of assortativity of clustering that can be calculated in terms of the latent variable or the visits that you observed in the network. Anyway, in this case, I also can build a simulation of the network, so it's not analytical. I can simulate the network according to the transition rates, the probability to join, and then I can choose one of the possible rules to join. No? There are many versions that make the hypothesis how a visit choose a destination. Okay, travelers. You can make many different choices. I will choose the most popular choice that give you the scale-free distribution of the visit. And the one is that the arrival rate scales as a power of the attractiveness, and I can get a sort of power law probability distribution of the visits in general, the frequency of visits weighted by the cost. And I have also in this case, with this typical choice, a neutral correlation, so a correlation that are spurious, just random. These are what is able to compare. So we have three ways to compute what we solve. I can use numerical mixture of distributions, so solve the integrals of a compound process. I can use a Monte Carlo simulation with agent-based rules, or I can just plot the asymptotic analytic distribution. I get quite similar result, both in the distribution, in the assortativity, and in the cluster. So the model represents the equations. It's not, it should be like that, to check every time. This is the real data. So I get data from your city for a given year, and they have origin destination matrix. So I go where I start and where I go. And this is the type of data that I have. I can compute, I can calculate the origin destination matrix. So I can essentially build the number of visits like that. So I have from a time window between 5, 6 in the morning, I have this quantity of people moved, then I add other visits until the 12 p.m. where the total visits come where they want to. And so the real data show these three behaviors that are the behaviors that I show in the simulation. This is a real world. You have a skillful distribution of the arrivals, of the visits. There are flat correlation, in the sense that the correlation, there is a correlation, but does not depend on the nodes. They're just random. And this is important, the choice of the variable. So here, for example, I have an important property that I can say that the trip cost, so include the trip cost in the visits, change the topology. The fact that they change topology means that the trip cost shape, in a sense, the distribution. In an analytical version, I go from a distribution like that to a distribution like that. From 2.2, I go to 1.8. So it means that there is a contribution of weights that scales with the visits in this way. Okay, and then I can estimate the contribution of the trip cost, the travel distance, for example, 5 minutes. Okay, and then we go to the data-driven side. So I have the model in which I have to choose the three variables: the arrival rates, the distribution of attractiveness, and the cost, the shape. I have many choices. Which one is better? And I want to estimate this one and compare with real world data. So there are many models. I know there are gravity model, radiation model, rank model. There are many models that try to do the same thing, but in a different perspective. So I use as an attractiveness, I use what is used called land use. Land use is the square feet of non-residential lots in blocks. I can give from data that I go to the administrative areas you can download, and I can assume that is the land use is already what is meant the location about, and from the data of the estimation of my attractiveness, I get these values 0.28. From this estimation, I apply also regressor analysis to detect the average value. And so choosing this one, I can calculate the degree distribution, for example, and it matches, absolutely, it matches what I got from the model. So using the model or using the latent variables, they are consistent in the calculation. Okay, I get 1.8, the 1.8 that I got from real data. And then this is what I got both from latent variables and from observed variables. And this is another possible way. I can use the trajectories rather than probability in order to get the way number of trips increase during the day. And then the last part is about the economic side. In the economics, it is important in transport economics, urban science, all this kind. The income, for example, I can study the relation between the income of the travelers and the cost of the travel. That, for example, in this case, is given in terms of travel time, how much time I get to arrive, and then I can calculate what is called income elasticity or travel demand. So the income elasticity, in some sense, is refers to how sensitive the demand for travel is to changes in incomes. This is calculated as a percentage change in travel demanded respect to a percentage change in income. And then it's important in economics because if this epsilon is larger than 1, it is called normal good. Normal good means that they increase proportionally one to another. Okay? Luxury, that more proportionally to the income, between 0 and 1 is a necessity good, like food or travel. If is epsilon is smaller than 0, is an inferior good. So it means that as incomes rise, people buy less of this good. So it's an important empirical variable in economics. Okay, just to share. And then I want to show the relation that there is between the study of all these latent variable estimation in terms of land use and attractiveness, hidden variables, and how this reflects on the income elasticity that can be calculated by any economist. They are very good on that. I put epsilon. Epsilon can be inferred by the hidden variable structure. Okay, so this is important because I can compute this variable from my hidden variable structure and compare with the literature of income elasticity for any transport mode, okay, because it depends on the transport mode, but this is very general. They are consistent, and I see that it is a necessity good. Okay, I finished essentially because there are all the implications that the economist can see in a work like that. The travel spending that can stimulate the economy, the generate employment opportunities, or because if the income increases, consumers may be willing to pay higher price for certain travel related services. So it's very practical. It's not only a model like that. To sum up, I have a urban ecosystem where scale-free spatial behaviors reverberates a different level of mobility. Okay, so a sort of scaling laws in general, from economics to fiscal policies, to physics, to mathematics. For example, this is a sketch. No, they are all related. There is no real cause and effect. There is a forward and backward causation in some way because it is a different scaling. Is they reverberates one another, and this is it. I'm finished almost in time. Thank you. If you have a question.
Thank you. There is time for one question.
So, Fabio, congratulations, you did a very good talk. I'm very much impressed. There are a few things that I didn't understand very well. When how you define the cost, yes, use the value of k denoted the cost, and then you wrote something p of k equal to I saw a power law.
A power law, yes.
So can you explain to me why the P of K has a power law involved?
PK as a power K is essentially the visits multiplied by the cost. Okay, each visit has a cost, so you can plot is a frequency, and you can see by data that is a scale-free distribution, so it's asymptotic power law distribution in which the number of visits are actually a fat tail distribution. The number of visits, how many visits this place has, how many visits a building like that has, you can plot, and you can see that it is a power law distribution. And this is not by chance, because it's how people decide to build the city. It's a consequence of that. It's not just so it's an emergent property of how people decide to organize the society, essentially. And in response of that, you can observe the number of arrivals in this place, the number of arrivals in other place. You can plot the number of arrivals, and you see a power law. That is space power law. Okay, in space, the number of arrivals.
Okay, we thank again the speaker.